Hey everyone, welcome back to the channel BugNoJutsu, your daily dojo for mastering algorithms with calm confidence and sharp precision. Today's problem is a brilliant mix of sliding window, greedy optimization, and heaps, one that will seriously level up your data structure game. We're tackling Leetcode problem number 2163, minimum difference between largest and smallest value of 3 subarrays. The twist? You have to split the array into 3 equal parts, and the goal is to minimize the difference between the maximum sum of any left part and the minimum sum of any right part. Sounds simple, but as you'll see, this problem dives deep. So make sure to watch until the end for key insights, optimization tricks, and practical intuition. Let's dive right in. You're given an array of integers with exactly 3 times n elements. Your task is to remove exactly n elements from this array, any n elements, not necessarily consecutive. After removing them, you're left with 2 times n elements. Now, split these remaining elements into 2 equal parts. The first half becomes the first part and its sum is sumFirst. The second half becomes the second part and its sum is sumSecond. You then compute the difference, sumFirst, sumSecond. Your goal is to choose the best n elements to remove so that this difference is as small as possible. That's it, find the minimum possible value of sumFirst, sumSecond after removing exactly n elements. Let's dive into a complete understanding of this example where the input array consists of the numbers 3, 1, and 2. The goal of the problem is to split the array into 2 equal parts, but with a twist. We are required to remove exactly 1 element from the original array before performing the split. Since the array has 3 elements, removing 1 leaves us with 2 elements, and that means we can divide it into 2 halves of 1 element each. So the key is, from the 3 original numbers, we need to decide which one to eliminate so that the remaining 2 can be split into 2 equal-sized parts, and then we calculate the difference between the sums of those 2 parts. The objective is to minimize that difference. To fully explore the possibilities, we'll try removing each of the 3 elements one at a time and observe what happens to the remaining values. Suppose we remove the first number, which is 3. That leaves us with just 1 and 2. If we divide this remaining array into 2 halves, the first half will contain the number 1, and the second half will contain the number 2. The difference in their sums, that is, the first part minus the second part, will be -1. That's our first possible outcome. Next, imagine we remove the middle number, which is 1. The remaining values are 3 and 2. Now, when we split this into 2 equal parts, the first part has 3 and the second part has 2. The difference in sums is 1. That's our second option. Finally, consider removing the last number, which is 2. The remaining numbers are 3 and 1. We split them, giving us 3 in the first half and 1 in the second half. The difference here is 2. So now we have all our possibilities, -1, 1, and 2. The smallest among these is -1. Hence, the optimal choice is to remove the first element, the number 3, because that leads to the minimum possible difference in the sums of the 2 resulting halves. This solution tackles the problem of minimizing the difference between 2 equal parts of an array after removing exactly n elements. The array size is always a multiple of 3, specifically, it has 3 times n elements. After removing n elements, we split the remaining 2 times n elements into 2 equal halves, and we want the difference between the sum of the first half and the second half to be as small as possible. Now, rather than brute forcing through every possible combination of n elements to remove, which would be computationally infeasible, this solution takes a smart approach using prefix and suffix arrays combined with heaps to keep track of optimal choices on both ends of the array. Step 1. Building the prefix array. We start by focusing on the first 2/3 of the array, i.e., the first 2 times n elements. The goal here is to build a prefix array, where each position stores the minimum possible sum of any n elements taken from the first I plus 1 elements. To do this efficiently, the algorithm uses a max-heap. A max-heap helps us always keep track of the largest elements among the ones we've selected so far. Since we want to minimize the sum of our selected n elements, we prefer smaller values, so if a larger value enters the selection, we consider replacing it. At every index within the first 2 times n elements, we continuously add numbers and maintain the size of the selected group to be exactly n. If the number of selected elements exceeds n, we remove the largest one, since it's least beneficial for minimizing the sum. The result is that, at every point, we know the lowest possible sum of any n numbers that can be picked from the beginning up to that point. This sum is stored in the prefix array at that index. Step 2. Building the suffix array. Now, we do a similar process, but in reverse, to build the suffix array. This time we look at the last 2/3 of the array, again covering 2 times n elements but starting from the end and moving backward. Here, the goal is to capture the maximum possible sum of any n elements selected from the current position to the end. So we want to maximize the second part of the array. To do this, we use a min-heap, which always keeps track of the smallest values among those we've seen so far. Why a min-heap? Because if we find a value larger than the smallest in our selected group, we can replace the smallest value with this larger one to increase the overall sum. This helps us gradually collect the highest possible sums as we traverse backward. The suffix array stores these sums at the respective positions, so we later know, for any point, what the best possible second half sum would be if we start from that point onward. Step 3. Finding the minimum difference. Now that we have both the prefix and suffix arrays, each capturing the best possible sum of n elements from the start and end respectively, we iterate through the middle section of the array. This is the exact area where the remaining 2 times n elements are split into 2 halves after removing n elements. For every valid split point, we compute the difference between the prefix sum, first half, and the suffix sum, second half. Out of all these combinations, we track and update the minimum difference found. This process ensures that we've considered all optimal combinations of picking n elements from the first and last 2/3 of the array, and have compared their difference in the most efficient way possible. The time complexity of this solution is n log n, where n is 1/3 the size of the input array. This comes mainly from the 2 passes over the array, one for building the prefix sums using a max heap and the other for building the suffix sums using a min heap. Since each heap operation takes log n time and we perform them over 2 n elements, the total heap processing time dominates at n log n. The final loop that compares the differences between prefix and suffix sums runs in linear time n, which doesn't change the overall complexity. In terms of space, the solution uses 2 arrays, prefix and suffix, each of size 3n, plus 2 heaps that grow up to size n. So, the total space used is linear with respect to the input size, giving us a space complexity of n. This makes the solution not only fast but also space efficient, considering we're tracking optimal subsets without brute force enumeration. Heap-based windowing. Instead of checking all combinations, we smartly track the best possible n elements using heaps, max heap for minimizing the first half and min heap for maximizing the second. This drastically reduces computation time. Prefix and suffix sum strategy. By pre-computing prefix and suffix sums at critical positions, we efficiently compare possible partitions without needing to recompute sums every time. Greedy optimization with heaps. We always keep the smallest n elements, for suffix, and the largest n elements, for prefix, that contribute to the optimal difference. This greedy maintenance ensures we're always working with the most promising candidates. Sliding cutoff point. The final loop smartly slides a virtual cutoff between prefix and suffix regions to determine the exact point of removal that gives the minimum difference, leveraging both halves optimized states. And that wraps up the problem. We tackled it with heaps, prefix-suffix tricks, and smart optimization. If you found this helpful, don't forget to like, share, and subscribe for more deep dives into tricky problems. Keep solving, and I'll see you in the next one.